Quadratic Trigonometric Equations. I almost start laughing as I say the title. No more intimidating title, I think, in all of grade 12 than solving quadratic trigonometric equations. It sounds like a lot, but actually it's not all that bad. See, first we're going to solve some quadratics, which we can already do. Yeah? I'll have to review that a little bit, but solving quadratics, that's not going to be a big problem. But apparently in all that, trigonometry is going to pop up. So if you did the last homework, you won't find this particularly, we're just putting together two skills we already have. But a great title, Solving Quadratic Trigonometric Equations. Let me read what the note says here. In the previous lesson, the trigonometric equations that we solved were all linear. In this lesson, however, we'll consider some nonlinear trigonometric equations, giving special attention to quadratic trigonometric equations. Actually, there's a couple that aren't technically quadratics, but we can handle them. Those are the least of your worries. So when learning to solve quadratic or trigonometric equations, it's often helpful to consider analogous equations that don't involve trig. What do I mean by that? This looks intimidating. Sine squared x equals 1/2. Or tan squared x minus tan x equals 0. And you'll find in the lesson, instead of thinking of them like this, I might think of this equation, x squared equals 1/2, and go, what would I do if it was x squared equals 1/2, and use that to attack this. In fact, I'll go a step farther and get ready for calculus with some of the methods I'll use and give you two options on how to handle every single question. So look at this one. This is like the high point of the lesson when we get to this one. Cos squared x plus 3 cos x plus 2 equals 0. Very intimidating, but we'll think of it as x squared plus 3x plus 2 equals 0, and that'll give us some steps to get started with. I might even use some substitution in here to handle it. Look at some of these. Tan cos squared theta equals tan theta. Looks impossible, you know? And then we'll think of it as xy squared equals x. I'll do this right within the lesson. This is more of a reference page. And again, if you don't have the note in front of you, that doesn't matter. What do you need to copy down? This, yeah? Let's start with the first one on the list, because that note says solve all of those. So it looks like a short note, but it's not. We're going to solve all of those. Starting with sine squared x equals 1/2. So to handle this thing, by the way, I'm going to try and color code this too. So when I go over and write in red, those are optional steps, which you might love, you know, these optional steps. Because when you first see this, and you see sine squared x equals 1/2, it might be too much to look at. But if you go over here and go, well, let's let y equal sine of x. And that bothers people when I do substitutions like that. It won't long term. We'll do substitutions like this all the time in calculus. But if you look at that and you're like, what are you doing? Maybe it's easier to think, picture sine x is equal to y. Just have that picture in your mind and it'll help you. So you go over here and go, that means y squared equals 1/2. And now your brain relaxes and goes, oh, I can do that. I can handle that. Y squared equals 1/2. What would I do here? I'd take the square root. And I'm going to miss a step here on purpose. You get ready. You figure out what step I've missed here. So I go square root 1/2. I can do even better than that. I can square root the top and square root the bottom. And I get something that hopefully makes you a little excited. When you see 1 over root 2, you go, oh, that's good. 1 over root 2. I'm in good shape there. What did I neglect there for that? Plus minus comes back to haunt you now. You know, so every time, if you're doing the opposite of squaring, you got to do plus minus 1 over root 2. So all of those steps, you could take this, and those could be your next lines in this question. You could just go there and do all of those steps. Maybe you don't need them. Maybe you're like, I don't need all of that. I'll go back to blue. Maybe you're like, yeah, I can do this right over here. Sine x equals plus or minus 1 over root 2. Maybe you don't need all of that. So the red all day is going to be optional. Almost like training wheels. You know, like, do I need this for this question? Actually, that's a bad analogy. It's not training wheels, because we're going to use this as a powerful technique. You know, so maybe every second one do it with the substitution, and then see if you can do it without as well. Doesn't matter. Okay, and once you get to there, this lesson is over. Now we're back to yesterday's lesson. Sine x equals plus or minus 1 over root 2. Well, plus or minus, that changes things a little bit, but not a whole lot. I'll show you what I mean by that. Here's yesterday's lesson. We want to know when sine x is equal to plus or minus 1 over root 2. Now let's talk about how I'm going to do the plus or minus. What quadrants, can you hear my voice laughing at what's just happened? Because I've set it up on purpose to be funny. What quadrants is sine either positive or negative? All of them. So for the first time this happened where it's like not just 2 quadrants, all the quadrants. And those of you who are starting to shortcut this a little bit and not do multiple diagrams, I'm not encouraging you to do that. I'm not saying, oh, you've got to get good enough where you don't need 4 diagrams. And that is not true at all. But those of you who are doing only 1 diagram for these, I saw on the test some of you are just doing 1 diagram to think this all through, then you might find this a little faster. But I like this picture. It really handles everything that's going on here. And let's teach a little of yesterday's lesson right in the middle here. So we're in every quadrant. We want the pluses, we want the minuses, you get all of them. Oh, let me go back to the question here. It says, use degree measure for the first 4. So we'll do the first 4 again. We'll do it in degrees to make sure we're not getting confused about degrees and radians. And then at the end, I'll do 4 in radians because I think that was unfair yesterday to do them all in degrees. I think it was the right thing to do, but it left you sort of shorthanded when you went to do radians questions. I'll fix that today. Anyway, so in degrees, opposite over hypotenuse is 1 over root 2, and hopefully you recognize the special triangle. There it is. So this is a 45. And it's the 45 in all of them. That related acute angle is 45 every single time. And now you're ready to answer the question. 4 answers instead of 2 now. X equals 45. I'm going to keep this lesson moving because I'm videoing it. But I do want to hesitate for a minute. I need somebody to explain again how I get this answer here, because then I'm going to skip that step the rest of the lesson. I'm going to zip right along through that. Just a reminder, how do I get that? The 180 minus 45. So whatever quadrant you're in, you just got to think through, okay, what's the related acute angle here? I'll rediscuss it when we get to radians, because radians has some special tricks there. So this is 135. This is 225. And this is 315. And I'll mention this from yesterday one more time. And then I won't mention it the rest of the lesson. Oh, that's not true. I won't be able to resist mentioning it. After doing this, you're like, oh, that's a lot of work. Okay, I did the plus or minus squared, did all the diagrams. Are they right? How would you know? How could you check this and move on to the next question on the test and not have to worry about this question anymore? It's a big moment. I'm willing to hesitate. How do we check it? Tia. Just plug it in. You got the calculator there. The calculator can't do any of this for you. But the calculator at the end, you can go, okay, sine squared 45, sine 45 times sine 45, and you'll get 1/2, and you're like, oh, it's good. Little check mark. You can put your own check mark on the test. There. I don't have to come back and check this one, saving you some time later. Okay. Any questions about that? I got to keep remembering. Do the first 4 in degrees to make sure we're okay, and then do the next 4 in radians. Okay. Yesterday's lesson built right into it. This is there. From there on was yesterday's. Tan squared x minus tan x. I got to get my reference sheet to make sure I know when we're at 4. Tan squared x minus tan x equals 0. Hard to look at. So when you see that, I'll switch over to red. You go over here and you go, let y equals tan x. If the let statement annoys you, because it does sometimes when you're first learning about let statements, instead write picture y as tan x. Just imagine tan x was y. What would you do here? You'd get y squared minus y equals 0. And what kind of, you hear my voice giving out, what kind of factoring is this one? I tried to be such a giant jerk about it for 3 straight chapters, so that when this moment came, you'd know what type of factoring is this? Common factoring. It's the best and worst one at the same time, right? It's the best because it's easy to do. It's the worst because it's easy to lose track of it and forget about it. So this is just y. Bracket y minus 1 equals 0. and then maybe you come back. Maybe that's all the work you need over there. Or maybe that's the work you do. I like it. This is a powerful enough method that if you just incorporate it right into your solutions, it's not like training wheels where you just get rid of it later. We'll need it at times. So what you end up with is tan x times tan x minus 1 equals 0. And now we're home. It may not be clear, but we're actually on to yesterday's lesson already. There's only two possibilities then. Tan x equals 0, or, look at me move over. See, I know this question pretty well. I'm moving way over because I'm like, oh, this is going to need a little bit of space. This one over here, tan x minus 1 equals 0. Maybe you jump all the way to here. Tan x equals 1. I want to know when tan x equals 0 or when tan x equals 1. Which one's easier? I don't know what the answer is. I'm not sure which one you think is easier. Which one do you think is easier? We'll do the easier one first. Okay. You like the 0 first. Interesting. When does 10x equal 0? How am I going to find out when 10x equals 0? That's supposed to be an easy one. The graph. Okay? Now, I have another option. Because if you're out there thinking, actually, you can even ask me this question after this. Does that mean I have to memorize the tan graph too? I'm okay with memorizing sine and cos. Do I have to memorize tan as well? And the answer is no. So just let that bounce around your head for a minute. Is there another way to do this? Now you get to find out if I have the tan graph memorized. Actually, I don't need the whole tan graph. I need this much. I don't need all the cycles of it. That'll be enough. Tan x equals 0 means x equals 0. Is somebody ready? Is there another way to do this without memorizing tan? Oh, look at he sees where I'm walking. Is there another way to handle tan x? It was the second way we learned how to graph tan. Is that what you're going to say, Ethan? You can just look where sine is 0. That's the same thing. We could have jumped another step here. I'm not suggesting it. But what I'm trying to get to is you don't need to memorize tan to be able to solve these questions. Sine and cos is enough. Because where sine x equals 0, tan x equals 0, and so I can get the answer right off the graph. These numbers are supposed to be easy when you see zeros, because you get those right off the graph. But we didn't do enough of them in chapter 6. We didn't do enough of the easy ones, so they seem like hard. Tan x equals 1. This one's hard. I avoided this in unit 6 because I knew how difficult this one was. I'll go through the whole procedure, and then we're going to need a little thought. This lesson, I try and put all the special cases in so nothing can trip you up. Cast rule. Hello?
Alexa McLean and Ethan Russell there.
Yes?
Could they both come up to student services for about 2 minutes?
Certainly. I'll try and drag my feet till you get back. Tan x equals 1. Oh, I'm acting like it's special triangles. Is it obviously special triangles? Why is 1 a special triangle? 1 and 1. Yeah? So easy it's hard. Or something. Or so hard it's easy. Or something like that. 1 over 1. I avoided that. It's like a tricky little one in the middle of all this. When it's root 3 over 2, 1 over root 2, it's like obviously special triangles. But this is the one case where it might not be obvious it's a special triangle, but it is. Okay, back to where I was. Great job. That was a good answer. Oh, that was good. Okay, tan x is positive. So in here and down here. And we figured out, was I still working in degrees here? One year I went to fix this lesson and put it on each question. Then I thought, no, it's better when you see me thinking about it. Every time I go to do this, I'm like, hold on. Degrees, radians. You know, you should be doing that every time you do a question. Am I in degrees or am I in radians? And I think I'm supposed to be in degrees here. So this is a 45 because we're 1, 1, root 2. And this is a 45 because we're 1 root 2. So my two answers are x equals 45. First quadrant angles are equal to the related acute angle, and this one is 225. Here, I'm going to highlight it. There's yesterday's lesson. The only thing I'm teaching today is how to factor this, which is hard to see, maybe without the y's. That's yesterday's lesson, solving the linear part of these. But do you have any questions? More time? Do you need more time on that one? All right. Still in degrees. Cos squared x, this is the one I talked about. This is like the high point of the lesson. If we can get past this one, the rest is like, okay, I'm starting to get the gist of it. Cos squared x plus 3 cos x plus 2. Does anyone want to take over and tell me what the let statement will be to help understand what the heck is happening here? The awkward silence. I'll take it. Feel the brains working. Feel the toast burning. What do you like as y here to try and picture what's happening? It's almost always the trig ratio you see most often. See here? When I saw tan, I just let y equals tan x. When I saw sine, I let y equals sine x. That's not a rule moving forward past this chapter. We'll have different rules all the time with this substitution method, but it'll often be let y equal the trig ratio you see there. And that'll make things nicer, because every time I see cos, I write y. I get y squared plus 3y plus 2 equals 0. That's really the analogous equation that I'm looking at. Picture it as y squared plus 3y plus 2 equals 0. Now factor this. Well, I hope it factors. Can you imagine if it was a quadratic formula in the middle of all this? I can imagine. Wait till you see. Okay. Two numbers that multiply to 2 and add to 3. Y plus 2, y plus 1 equals 0. You can come back over there anytime you want. Maybe it's here. Maybe you want to go another step. Maybe you want to go, therefore, y equals negative 2 or y equals negative 1. I really like there. That's a good moment to come back. I'm in great shape now. I've isolated both. So when I come back, and by come back I mean get back to cosines, because this could be your steps. You could have this line, then do this, do this, do this. It's powerful stuff. It's useful in calculus, that kind of thinking. Come back over here, and so I get cos x, not y, cos x equals negative 2, or cos x equals negative 1. To which I ask the same question. Let's do the easier one first. Which one's easier? And I don't know the answer. I don't know which one you're going to think is easier. Which one do you think is easier? Which one looks familiar? I agree. Cos x is negative 1. I mean, the cos x graph's right on my sideboard there, but I'm going to draw it. When you see negative 1, that's supposed to be an easy question. But I won't lie. It's sometimes a little bit harder because of the way we've taught these chapters. We did a lot of the tough ones. We didn't do enough of the easy ones. Here's a nice easy one. Cos x equals negative 1. Where am I? Am I still in degrees? Still doing this in degrees. Okay, so in degrees. I guess I didn't need to ask that to draw the graph. Here's the... I don't even need a really good graph. Just an okay graph to remind myself what's going on. Cos x equals negative 1. So in degrees, this is 360. This is 180. This is 90. This is 270. As we move along, you might get so good at cos that instead of drawing it, you just in your brain go, and you can do it like that. But you don't have to. Cos x is negative 1. There it is. X equals 180 degrees. Only one answer that time. Yesterday, maybe it was the other class, someone said, oh, you always get two answers. And I agreed with them. I said, yeah, you always get two answers. And I just played along, and I went, it doesn't have to be. Sometimes you can just get one, depending on what you're looking for. Okay, Cameron said this was the easier one. Or the more familiar one. I changed my question, didn't I? This one's actually easier. When does cos x equal negative 2? What's that? In our hearts. It never gets there, does it? And so if maybe you're stuck on the test. This is going to happen to people on the test. They get their calculator and go, I don't know the answer. I'll do that cos inverse trick. So you go cos inverse of -2. You punch it in your calculator, and your calculator goes error. And the calculator's trying to tell you, you better check again because that's not happening. That doesn't occur. So there's no answers here. So yesterday when someone said, there's always 2 answers, I was like, well, I guess we'll talk again tomorrow. Because yesterday there often was 2 answers. It was often 2 answers we were looking for. Here I got 1 answer, and I got no answers out of this, because cos never gets to -2. What questions do you have about that one, though? Oh, let me underline again. There's yesterday's lesson. Once we got to there, that's yesterday's lesson. I'm doing some extra special cases, but we were back to linear. And maybe that's a better explanation of all of high school. Quadratic was about breaking it into 2 linears. That's what we'll be about. We'll break it into 2 linears, and then we'll go from there. Questions? More time? Who needs more time? Oh, here we go. We got to get somebody in on this y. Is this the last of the degrees? Last of degrees. Okay. What do you want the let statement to be to try to follow or try to get an analogous equation that I have a chance at? I won't lie. Some of you will get good enough at this. You'll be like, I don't need your crazy let statements. I can see what's happening. Boop! Factor. You might be able to do that. So if you can do that, wonderful. You don't need these other steps. What do you want to imagine as y to get a chance to understand this, though? It's usually that trig ratio, yeah, that you see in the question. There's only signs in there. What if there's other ones? What if it's not just sine? Oh, let's keep our stick on the ice for just a minute here. Let y equal sine x, and what I get is 3 sine x, sine squared x, sorry, 3y squared. What am I doing? I'm substituting. 3y squared minus y minus 2 equals 0. Does it factor? Does it factor? You're like, oh, please let it factor. Imagine a quadratic formula pops up its head in the middle of this. Maybe it does anyways. Maybe you're like, I've never been good at factoring these. I'm going to have to use quadratic formula on this thing. So you're stuck with quadratic formula. But this one does factor. I don't know what method you're using at this point. Let's see. This is my method again. 3y squared. This must be 3y and y. So this has got to be a 2 and a 1. 2 times, how's that going to work? It's got to be 2 and 1. This is 2, 1. 3y minus 2y. No, negative 3y plus 2y. And of course, I've done a million of them, so it doesn't take me long to get these things figured out. Maybe it takes you a little longer, but that's my method. It's just like, just make it work out. 3y squared minus 3y. Look at me checking, even after all these years. You know, doing that FOIL thing to check to make sure it's right. And then so I get y equals negative 2/3 or y equals 1. I like that moment. Of all the moments to switch back, that's the clearest to me. Get y figured out. In this case, it's actually get sine x figured out before I come back. Sine x equals negative 2/3 or, ooh, look at me reading the situation, or sine x equals 1. I've given it away by how I drew this. But which one's the easier one? Because this is bad. This is reteaching yesterday's lesson right here. Sine x equals 1 is right off the graph. So you draw yourself even a tiny little graph just to remind yourself, okay, sine x goes like that. Sine x equals 1 is right there at pi over 2. No, am I still degrees? Yeah, let's go through your mind the whole time. Every time you do a question, like, am I degrees? Am I radians? So there's 90. So over here I got x equals 90 degrees. Only one answer this time. Well, and now we got to talk about yesterday. Sine x equals negative 2/3 is 2 over 3 in a special triangle. I'll let you think about that while I draw the standard equipment here. watching the video. You should even pause the video and go, do I know the answer to, is 2 over 3 in a special triangle? Is 2 over 3 in a special triangle? No, it sort of feels like, because it's got a 2 and a 3, but it's not a root 2 or a root 3, so it's not in a special triangle. So how do I make it special? Who's got this from yesterday? I want that related acute angle, and I can't use special triangles to get it. Sine inverse. So we want them exact if we can. You're going to see that soon on the tests. In September, when you see the test, every test will say at the stop, do exact if you can. If you can't, do 2 decimal places. And now it'll be up to you to decide if you can. And here we can't. We got to do sine inverse of 2/3. As I get out my calculator, in degree mode, sine inverse 2 divided by 3. I get 41.8. I'm only taking the extra decimal place so that you can see if you get the same as me. Normally we go nearest degree. Degrees are really small. We can go nearest degree. Now, I did something there. Did I forget the negative? Seems like I ignored it. Where does the negative get taken care of? The Castrol's taking care of the negative. The Castrol's like, don't worry, I'll do the negative. Don't confuse yourself, just do the positive. And if that bothers you, stay tuned. In November, we'll talk a little bit more about why this is a good move. We might actually keep this move, actually. I think the calculus people just keep this move, but they understand a little bit more about why we don't tread into the negatives with the sine inverse button. Well, it's simple. The sine inverse button gives one answer. We don't want that one answer to confuse us. We want just the related acute angle. So now I take care of the negatives. I go over here and I go, okay, sine negative quadrants. There and there. And in the picture, I'm just going to use the rounded angle, because nearest degree is almost always good enough. Degrees are very small. Not that it would be wrong. If you wrote 41.8, I'm good with it. But 42 is better for the picture. So my 2 x values are 222 or x equals 318. And I said I wouldn't ask again, but how did I get 318? Where's that coming from? I'm barely even drawing on the pictures now. We're supposed to be good enough to... 360. Yeah, 360 subtract 42. And some of those little things that were a problem in Unit 6, maybe we've seen enough time. That's why so many people like rewriting Unit 6. Because some of this, as we do Unit 7, you're like, oh, I totally get that now. 318. I don't know why that was a problem. But it is. It's a real big problem in Unit 6. And not till we do more practice in Unit 7 does Unit 6 become more clear. Okay, you got... Okay, one thing about subbing. If I sub in 90, I'll get, when I do 3 sine squared 90 minus sine 90 minus 2, it'll say 0 in my calculator. If you use 222, it might come out to 0.002 or negative 0.001. Because I rounded off, my answer will be rounded off. So don't let that freak you out. If you've used rounded answers, you might not get exact checks. Yeah? What questions do you have about that? Oh, I got to reteach yesterday's. So if yesterday's lesson went by you or you missed it, there's what we did yesterday. Linear trigonometric equations. More time there? Oh, we're in great shape time-wise. What, I got the 4 rating ones and the 2 bonuses to go. We should be okay time-wise. This is not a quadratic. It snuck in the quadratic lesson because it is still factoring. What type of factoring is this? It's common factoring. I'm going to do one without the y's because the y's aren't quite as helpful in this one. Common factor out the sine x, and I get 1 plus 2 cos x. Actually, seeing that might help a little more with identities. During identities, we wanted a common factor sometimes. Take the sine x out of both of those, and so I get my 2 linears. Either sine x equals 0 or 1 plus 2 cos x equals 0. And again, yesterday's lesson, that was another thing that came up in yesterday's lesson. Sometimes we had to rearrange this linear equation. So bring this over, divide by 2. I get negative 1 over 2. Which one's easier? Zero, 1, negative 1. Those are all easy. I'll go back to my previous graph. Where is it? Sine x equals 0. There's my sine x graph. Sine x equals 0 means, therefore, x equals 0. This one, though, needs a little bit of work. 1/2 is 1/2 in the special triangles. You think about that. I'll get the grids up. Negative, negative. Sine quadrant, tan quadrant. Remember when this was the toughest question on the whole test in Unit 6? Maybe it wasn't the toughest, but pretty close. Yeah? I'll actually draw it on there. Adjacent 1, hypotenuse 2. Adjacent 1, hypotenuse 2. Is it a special triangle? With 1, yeah, it is. Okay, so this is root 3 over here. And this is root 3 over there. And now's the first time I asked myself, was this degrees or radians? I didn't even have to ask myself over here. 0, 0. In degrees or radians, 0 is still 0. But now it's, so what did I say? I was going to do the last 4 in radians? And this is number 5. So yes, okay, so in radians. So this is a pi over 3 in the special triangle, pi over 3. So my x value is blank, or x equals, and let's go over this one more time. Ethan had a method yesterday to handle this. I mentioned a method. Will somebody else explain how they know what this angle is? What is it you do in your brain to figure out what this whole angle is if that's pi over 3? Couldn't tell if she was. Hannah's going to go. Hannah, what do you got? I like that. It's the simplest way to handle it. Think of this as pi, which is 3 pi over 3. And if that's 3 pi over 3, this was 1 less than that, which is 2 pi over 3. That's a powerful way to do it. Not as efficient as Ethan's method, I think, but powerful. And so this one is 4 pi over 3. That's almost identical to the one that was on the Unit 6 test. Any questions about that one with common factoring instead of quadratic factoring? It's not quadratic because it doesn't have a squared in it. But it's still part of that type of thinking. More time on that one? Hopefully you kept up with copying. You're with me? 3 more in radians. 3 more in radians. Keep reminding myself. Cotan x. Oh, good. You're thinking, thank goodness cotan was in this lesson. I was really hoping cotan would appear. Cotan, cos equals cotan. Well, this has multiple steps. I got to get all onto one side. Let's rewind all the way to grade 9. Grade 9 was get x's on one side, get numbers on the other. After that, equation solving wasn't the same anymore. It was get all to one side with 0 on the other. It's the only way factoring could help, was to get 0 on the one side. Oh, I've seen some nodding there. That's why I put that ridiculous question on the test. I said something about, why does it have to have 0 on one side? It's the only way factoring can help. Now I can factor. Common factor, cotan x, cos x minus 1. And so I got these two different pieces. Cotan x equals 0, or cosine x minus 1 equals 0. This one I think is the easier one because it's cosine. So go after the cosine graph. I don't think the cosine graph is anywhere else in the note. It might be, and if it was, I could just reference it. But cosine x equals 1. Radians? So this is 2 pi. So x equals 0 or x equals 2 pi. Good. I did that quickly because I want to focus on cotan x equals 0. Because I would agree with you if you're like, are you kidding me? I mean, I got to memorize now the sine graph, the cos graph, the cotan graph, the tan graph, the secant, the cosecant. I got to have all those memorized to be able to handle these things, and the answer is no. I'd really have to think for a minute to memorize the cotan graph. Yeah, I could do it. But it doesn't come up enough to be useful, to have it in my memorized bank. What can I do here to make it so I can handle this situation without having to graph cotan? It's going to stop me. Wherever cos is 0. Where are you getting that from? How do you know it's where cos is 0? Yeah, because cotan is cos over sine. You're going to have that trig toolbox with you. So you can always just go, okay, this is cos x over sine x equals 0. And the same graph will help you. Where's cos 0? Pi over 2, 3 pi over 2. So x could be pi over 2, or x could be 3 pi over 2. So I like that. I like that better for tan and cotan, me personally. Just go to sine and cos and look for the answers off of there. What questions do you have there? More time? Do I get 2 more of these left? 2 more of the regular ones. Okay. Cos x times sine x equals 0. I threw this one in there because it might cause you trouble. This is already factored. There's nothing to do here. Either cos x equals 0 or sine x equals 0. I seem to remember in my head, this wasn't part of the lesson when I first started teaching this. I added this later because some people had some trouble in the homework when they saw this. Because they're looking for factoring, right? You're looking for the difficult thing. And sometimes the easiest question causes you the most trouble. Cos x equals 0, just look at the graph. That's at, I can go back to my last page. When does cos x equal 0? That's the same as the last one. X equals pi over 2. 3 pi over 2. When does sine x equal 0? Go back to my graph. Oh, I don't have a full sine graph. 0, what would that be in radians? What are those other 2 in radians? Pi and 2 pi, yeah. So those graphs, you might have to write them in radians. Some people, when I hand them the test for this chapter, just flip it over to the back page and immediately draw sine and cos in degrees and radians and just refer to that during the whole test. You'll get to the point where you just got to memorize. You won't be able to help it. Even if you don't want to memorize them, you'll memorize them. So let me just write a note on here so you have it. Look at the graph. And I hope I've convinced you that moving forward, memorizing sine and cos will be enough for us. We won't have to memorize the other ones and have them at our fingertips all the time. Questions about that? Easy/hard question. It's hard because it's too easy. And you're looking for trouble. You know, the questions like this on a test bother people because they're like, is that really all I have to do? It doesn't seem like it, you know. One more of these, am I right? And then there's 2 special ones at the end. Then we'll need some extra brain power. We'll have to flip on all the lights then. Because this one isn't any harder. Oh, no, this is. Oh, this is a great warm-up question. Okay, step 1. What's the basic problem here when dealing with these type of equations? It doesn't have 0 on one side. So the first move is bring this over. Seemingly a lot like previous questions. And it has common factoring, which is nice. I'm not torturing you with a bunch of different factoring questions here. Common factoring. Am I done factoring? No, Cameron says. Yes, someone else says. I'll say maybe. I could handle this with factoring. I could handle it with isolation. What type of factoring is this if I wanted to factor it, though? It's a difference of squares. That was the nice thing about this 1 minus cos squared identity is it came up difference of squares. This has changed sign, but it's the same thing. So you could handle it like this. This is a nice, easy way to handle it, is to go cos theta plus 1, cos theta minus 1, and now it's 3 different factors. And you're like, oh, okay, so now you've really sort of gone to 3 factors, which we sort of saw in the previous chapter. So we can tiptoe into this a little bit, having 3 factors. So I need tan theta equals 0. Or cos theta equals negative 1. Or cos theta equals 1. Each of those pieces. These ones right off the graph. I'll redraw the graph here of cos theta. Cos theta. Here it comes. In radians, no less. There's 2 pi. There's pi. 3 pi over 2. Pi over 2. When is it equal to negative 1? Pi? When is it equal to pi? Positive 1? I did that quickly because there's been previous questions that did finding 1s and negative 1s. How about tan theta? It's decision time. Are you going to memorize the tan graph? Or what's the other option? How could I immediately switch this to get it to something that I don't have to memorize new stuff? It's right in the trig toolbox. You look up and you go, what's tan? Sine over cos. Okay, so sine theta over cos theta. So I want to know when is sine theta equal to 0, and right from the graph I get theta equals 0, pi, and 2 pi. I'll be honest, I find sine easier to memorize. 0, pi, 2 pi, that for me personally. Cosine I always have to think a little bit more. I got the same answers both sides here. That's just a random coincidence. I wasn't trying to prove some point there. That's just the way that question happened to work out. But what questions do you have there? More time? Okay, well, you're at that point, maybe you're like, you oversold this lesson. You acted like it was so tough, and it's just a little bit of factoring, and that's the same as yesterday. To which I say, yeah, I know. I did all that to really show you this. This is what I wanted to get to. Solve the following using degrees. Okay. Negative 10 cos squared minus 3 sine x plus 9. Why is it that this cannot be factored the way it sits right there?
Because you have a cos and a sine.
You have cos and sine, and that is disheartening. When you see that, you're like, cos squared and sine all in the same question. If only there was a way to convert cos squared over to sine squared, then we'd have a chance. Is there a way? Now you can understand the order of the chapter now. We had to do identities first if we were going to get a chance here. Cos squared is 1 minus sine squared. Again, noticing, remember, these were the useful 2 little brothers on here. I hand you your trig toolbox on the test. Can I borrow yours? I hand this out in the test, you get this. You immediately go, right underneath there, you go, doo doo, and remind yourself, that's not the useful version. Well, it sometimes is. Mostly, these are the useful versions. Cos squared is 1 minus sine squared. And at that moment, it's not time to order pizza. But it is time to get the flyer out of the drawer and pick out what you're going to order, because this is almost done. Now it's all sines. You're like, oh, okay, at least it's all sines. I mean, it's still a big mess, but at least it's all sines. Let me show some work that hopefully is not too bad. Distribute that negative 10 in, and then sort these terms out. And then cold panic sets in. Can I factor it? Can I factor it? Well, at least try. You won't know if it factors until you try. Oh, that's a 1. Oh, when it's a 1 there, at least we don't have a zillion possibilities to think about. This has got to be plus 1 and minus 1. Okay, well, now, if it's going to factor, it's got to be plus 1, minus 1. Two things that multiply to 10 and add to negative 3. Oh, this one was nice. Oh, he made them factor. Okay, at least it factors. Okay, so 2 cos x and 5 cos x. Let me check that. 2 cos x times 5 cos x, 10 cos squared x. Negative 2 plus 5. No, that's not right. It's the other way around. And that's exactly how I factor. You can have your own method, and if you do, great. My method involves just playing around, getting the numbers that work, and then multiplying out to check if it's right. Yeah? So I get 2. Am I going to have enough room down here? Cos x equals negative 1/5, or cos x, equals 1/2. Which one's easier? Actually, this is a good question. Which one is easier? Are you going to be happy to see the special triangles now after all this? Or are you going to be happy to go, no, I don't want to have to do the special triangles? I'll do the special triangle one first. Not because it's easier, but just to establish what the heck I'm talking about there. Cos x 1/2 CAST. Check the clock. Oh, yeah, we're in good shape. Straight line, red. Okay, so positive cos. A, C. Good. Adjacent over hypotenuse. 1/2. 1/2. Is it a special triangle? I mean, hopefully you saw before you got to there, but maybe it takes all the way to there and picturing it before you go, oh yeah, special triangles, that's √3. √3, exact if we can. So that's pi/3. That's pi/3. So I get x equals pi/3, or x equals 5 pi/3. Is that the easier one? Like, is 1/5 in a special triangle?
Did I miss something, or why did it change into cos?
Oh, okay, now, good moment. I'm not glad I made that mistake, but a good moment when it happens. A lot of the homework before now, sometimes you make a little mistake like that and you're like, erase, and you just erase everything. Sometimes we can recover. I can recover here. That wasn't supposed to be cos. That was supposed to be sine, but I can recover most of it. Right up into the answer. So this was sine x, and this was sine x. So then when I went down to here, those triangles are going to be wrong because it's opposite over hypotenuse. These had to be, let me fix those up. Good. And those angles are going to be wrong. Good. Okay. So, more erasing. Fix that up. I'm sure that angle's going to be wrong now. So it was opposite over a hypotenuse was 1/2. So the √3 was there, and that's pi/6. Answer is pi/6. Or, what is this one? 2 pi is all the way around. So that's 12 pi/6. That's 11 pi/6. Thank you, Ethan. And these were signs up here. Yeah. Oh, yeah, good. Another error. Yes? Sine x is 1/2 in this quadrant here. So this has all got to go. That's why it's not 11 pi/6. Get my big eraser out. Grab this out of there. Sine is positive in this quadrant. Which quadrant is it? Here. I'll relabel the cast rule on there. Opposite hypotenuse, pi/6. So 5 pi/6. And actually this relates to a conversation I had with a couple of period 4 people yesterday when they got their test back. And at first they were upset with their mark because they had lost a bunch of marks Then when they got the test back and read it over, they went, oh, it was just silly little stuff like that. Like, you know what I mean? Like stuff where it's like, oh, yeah, I knew that. How did I mess that up? And when that happens, you don't get too upset. I mean, it's annoying. Those are annoying marks to lose in the test, but they're not ones to lose your brain over. You get to a question where you either left it blank or you totally didn't have the idea at all, then it's not panic time, but it's time to restudy some of that and figure out what the heck is going on about why that's happening to you, okay? Would I have caught it? There's the next big question. Would I have caught the mistake? Torrance skeptical. She's like, I'm not sure you would have caught it. What could I have done that would have caught this? If I'd have taken those things in the end and subbed them in, it would have gave me a chance at catching it. Because it's easy to miss a mistake like that and never see it again. Never look back at it and just continue on because your brain's somewhere else, right? Okay, nice catch. Back to here. Is 1 over 5 in a special triangle? No. So I got to do this sine inverse move. Give up on getting exact answers and go to sine inverse on this. Oh, I got to be in radians. Oh, this. Am I in radians? No, degrees. Oh, okay, let's go back to that. I'm going to do it all in radians, and then at the end we'll go, whoops, I made a mistake, and we'll talk about converting. Sine inverse, I'll do this one in degrees. 1 divided by 5. 11.5 degrees. Oh, that's an awkward angle. 11.5 degrees. Hard to know whether to round up or round down. You think about why did I ignore the negative? Actually, it's not true. I didn't ignore the negative. Why did I not type in the negative? Write down the cast rule. C-A-S-T. C-A-S-T. Sine negative. Okay, there and there. Totally giving away the answer to my question as soon as I said that out loud. So I get 11.5. Tough to draw in my diagram because I made them so small. Here, 11.5, 11.5. So I get x equals 168. No, add 11.5. 191.5. Or x equals 348.5. I did those in degrees. So what should these have been in degrees? This would be 30 or 150, because this question asks for us to do it in degrees. Okay. Why did I neglect the negative? I didn't ignore it. I neglected it because the cast rule is going to take care of the negatives. So leave that out of there when you see negatives in there. Mr. Todd, would there be one like that on the test? I know you love asking that question. I don't know whether it's to try and avoid doing the homework or what. And I'll get the red highlighter out and say, yes. That's two things at once, right? It's one, it's bad news, but it's also good news because you're like, if I study this, it will pay off. Will you have to do a substitution within a quad trig? Yes. Does that make you now have questions about that one? More time? I'll do this one in radians, okay? I know the worksheet says do it in degrees. I'll do it in radians because I think I did a disservice to you yesterday by doing everything in degrees. We should be able to handle radians when it happens here. Secant squared x plus 5 tan x equals 2. Will there be one with this kind of substitution in the test? No. No, no. This is only there. Don't skip over these in the homework. We do the difficult ones so that when the test comes, those ones seem easy. Okay, so don't ignore these. Just be aware as you're battling through a tough one like this that it's not a test type question. I've never gone to this identity. Can anyone see the identity I'm going to need here? What's the problem? Why can't I factor this? Because there's secant and tan. So I can bring it over. Secant squared x plus 5 tan x plus 2 equals 0. I can bring it over, but I can't factor. And there's another identity in there. It doesn't come up very often, but I threw it in there today to sort of get ready for calculus. There's a relationship between sine squared and cos squared, but there's also a relationship between cotan squared plus cosecant squared, and one between tan squared and secant squared. So I can replace that secant squared with tan squared plus 1. Scary stuff. Calculus level stuff. In fact, actually, AP calculus level stuff. Not too many times this happens in regular calculus. Where'd it go? Secant squared. Tan squared x plus 1. Did I do it right? Tan squared x plus 1 plus 5. Yes, okay. And then just rearrange. So now I just factor this. What two numbers that multiply to 3 and add to 5? What two numbers multiply to 3 but add to 5? There's no two numbers that no, there's no two whole numbers. There is two numbers, but they're decimals. How do I solve a quadratic that won't factor? The quadratic formula. Can you believe that? In the middle of a quadratic trigonometric equation, the quadratic formula. It's actually not that bad. Wait till you see what has to happen here. It's not as bad as it looks. Watch the quadratic formula here. Tan x equals negative b plus or minus the square root of b squared minus 4ac. Once you get past your annoyance that the quadratic formula has appeared here, you write it down and you go, okay, let's plug these in. The b is 5. The a is 1, and the c is 3. I mean, ignoring the fact that it's tan x sitting out there, life is not too bad here. It's just the quadratic formula. And we talked about, with quadratic formula, I want to see the subs. I want to see that step here. But then you got the calculators for this. Just punch that rest into your calculator and get those two answers. I'll break out some power here. Okay, so especially you got your fraction calculator, your Casio. You know, these are not too bad to type in anymore. Negative 5 plus square root 5 squared minus 4 times 1 times 3 all over 2 times 1. I get negative 0.70. And then I go back and change that plus to a minus. And I get negative 4.30. And if you don't like special triangles, this is good news. Because neither of those are on special triangles. And you see, I didn't have to, I skipped all the factoring, skipped all the drawing, everything I had to do there to get down to that point. Life is good. How do I get, I need, well, how many diagrams am I going to need here? 4 different diagrams. I'll draw them out, and then I'll let you think about that next step, because that next step was new yesterday. Well, what has to happen? Ooh, a little lower. Make space here. There. Oh, this active board. It's getting old. See that? Gonna need a new one soon. The pressure in the room just changed. Did you feel that? Anyone else's ear pop there? Gotta open the window. All right, there's all the diagrams. New from yesterday. Those are not special triangles, so how am I going to get those related acute angles? It's nice. It's nice, actually. Tan inverse. And if your attention span has wavered, I totally get it. It's a long lesson, but you might want to come back for just a minute. I got to do tan inverse 2 times. Ignore the negatives. That's fine. But I said do this question in radians. And it could be that your strategy is, no, I'll do it in degrees, and at the end I'll do it in radians. And it's okay. It's not the greatest, though. We'd love to be able to do this in radians. So I'm going to show you how to do it in radians. Here's the related acute angle. Get my calculator, make sure it's in radians. Because something freaky is going to happen, and we got to be ready for it. Oh, I don't even know how to do radians on this guy. There, okay, radians. Okay. Tan inverse of 0.70. 0.61. And if you're not ready for radians, that might look weird. 0.61. We're used to degrees being 20 degrees, 30 degrees, 50 degrees, 80 degrees, and 0.61 might freak you out. And that's when you might change your strategy. Like, maybe I'll just do this in degrees and convert it at the end. Well, we can manage 0.61. And this one, I'll do this one first, and I'll go to this one. 0.61. I've got to be in the tan negative quadrants. So, not to make my diagram too messy, CAS, CAST, no, tan down here. There we go. So that angle 0.61. And now we need somebody very brave and right on top of this to go, how do I get my 2 answers here? X equals 0.61. Looks weird, but it's right. 0.61. How do I get this angle here? In radians. Your brain screams, well, if it was degrees, it'd be 180. But it's not degrees, so what is it? It's pi. So we go pi minus 0.61. So if you're having trouble and you're doing these still in degrees, it's only one little leap to be able to do them in radians. And so when I do it in radians, I get pi minus 0.61. I get 2.53. And this one would be 2 pi minus 0.61. So I type that into my calculator, 2 pi minus 0.61. 2 pi minus 0.61. 5.67. It looks weird, right? 5.67 looks weird because you're thinking in degrees. But 5.67 for radians, I mean, it's only 6.28 all the way around. So I'll do it one more time over here. Tan inverse of 4.3, I'll write it over here. R equals tan inverse 4.3, 1.34, which looks completely weird. But for radians, it's okay. And if I want the tan negative quadrants, it's the same. Both were negative. Oh, isn't that interesting? This question worked out that it was the same quadrant. So here and here, related acute angle, 1.34, 1.34. So my x is pi minus 0.34, or x equals 2 pi minus 1.34. Whatever, 0.34 there. I'll type those in. And then I'll pause for questions because that was a big bite we took there. Checking my notes. Is that the last example? Yeah, that was the last example. Would I put a quadratic formula one on the test? No, we don't have enough time. In an hour and 15 minutes, I can't be, dropping all that on there as well. It was bad enough having one with substitution in there, which I said would be there. I couldn't turn around and then also add quadratic formula in there. So there's just never time for this. Should you do it in the homework? Oh yeah, because if you can do this, see how it's every question in the chapter is right there. The whole chapter is in one question. So if you can do this, you're ready for whatever I throw at you on the test. But do you have questions about that, how that ended up there? More time? All right, let's talk about the website really quick. and your schedule. I want to talk about the next few days, right? No, website, stop the video, and then schedule. Let's go. What's today? Do I know what today is? Tuesday, May 17th. No video there yet. I'm making it right now. So next time you look, the video will be there. A completed version of the note, homework, and again, supplementary problems in this section again. If you can do these and it's going okay, you don't need to do the supplementary problems. Or maybe you want to poach the supplementary problems. You're like, oh, I still don't like those substitution ones, and he said it's on the test. Go in there and find where in there there's a couple of substitution ones you can do, okay?